name is Mike Resso, and I'm a Signal Integrity Application Scientist at Agilent Technologies. Today I'm going to be talking about test methodologies for optimizing the design of 28 gigabit per second and higher channels. Specifically, we're going to talk about backplane differential insertion loss and how to do some curve fitting with MATLAB as a new feature of physical layer test system software. As we know, the future trend of data rates is getting faster and faster, and I think the most interesting work for signal integrity engineers is going to happen between 10 gigabit Ethernet and 100 gigabit Ethernet. And this is in fact where we are today with our high-speed digital design. There are compliance standards today that we're designing to that are exactly in this realm of 10 to 100 gigabit Ethernet. So we know that impedance problems are everywhere. Backplanes, IC packages, PC boards, connectors, and cables. And anytime we have reflections from these impedance problems, it's a bad day in the lab. And so we want to try and avoid these types of non-uniform impedance environments, because that's a hindrance to conducting high-speed data through our differential channels. So when we can design for high speed, that means we avoid any type of impedance problems from any type of transition from a coaxial connector into a planar PCB or otherwise. So we know that we can design a printed circuit board very keenly for very high speed, but we don't always know how the manufacturing of that board is going to come back to us. And so I've created a graphic here with a cross-section of a printed circuit board with just some of the typical problems that we can encounter in the manufacturing process. As we look at this vignette number 1, you can have excess capacitance in a through hole. And number 2 here, you can have localized crosstalk between a differential pair and vias. In 3, you can have localized changes in conductor width, which would create some excess inductance, this differential impedance discontinuity. In number 4, you can see we have localized changes in the conductor spacing. Simple solder splash on one trace and not the other will create this type of impedance mismatch. Number 5, we have reflections due to via stubs. Anyone who's designed backplanes can attest to this problem. And you can avoid that by doing back drilling or using micro vias, things of that nature. 6, we can have non-uniform dielectric material. Anytime that dielectric is non-homogeneous, it's going to cause problems in impedance. And 7, we can have surface treatment thickness non-uniformity. And 8, we can have localized changes in foil thickness. And in this 9, this is something Bell Labs discovered. You can have anodic conductive filament shorting, which actually produces the migration of copper ions between layers in a board. So all of these things are possible problems in the manufacturing of a PCB, and we need to be able to troubleshoot these in case we encounter any of these problems. Now, if you're only going to remember one slide in this whole presentation, I would say this is the one. Differential S parameters are what we use to characterize and obtain compliance information for differential channels. And so here we can, for a 4-port differential measurement, we have 4 quadrants. Quadrants 1, 2, 3, and 4. And quadrant 1 is probably the most common because it's differential stimulus, differential response, and this is how the device is used in the real world. Quadrant 4 down here is not so important. It's common stimulus, common response. But 2 of the most interesting quadrants, I believe, are quadrants 2 and quadrants 3. These are because these 2 quadrants are called mixed mode S parameters, and anytime you have any non-zero magnitude levels in these parameters, that means you are converting one mode of propagation into a different mode, and that's not good. That's going to be indicative of crosstalk, either susceptibility or emissions, and so we have to be very careful about doing that. In fact, with something like PLTS software, not only can you measure the magnitude of crosstalk, but you can locate the spatial location of it inside the channel when you use these powerful mixed mode S parameters. Here's a typical frequency domain analysis looking at insertion loss of 3 differential channels. And you can just see it's basically the frequency response that is seen by a differential signal as it propagates through the differential channel. So it's simply frequency response is an easy way to think of this. In some of our compliance standards, like I want to say 802.3, there are some polynomial fitting that goes on for differential insertion loss, and this curve fitting is done quite a bit in MATLAB as a separate operation, and this is the least mean squares fit polynomial best fit for insertion loss, and this is what's done in 802.3. Another example of curve fitting is this right here for differential insertion loss again. In this case, you can see not only do they give you the formula, but they give you the coefficients for each of the terms. And this happens to be from 50 megahertz to 15 gigahertz. In addition to curve fitting differential insertion loss, there's another term that's very important, and this is called insertion loss deviation. Insertion loss deviation is simply the error relative to the polynomial fit to the actual data itself. And so this is what we call insertion loss deviation. And this is another calculation that's commonly done in MATLAB. Just to give you a very clear point of what we talk about when we say the channel, if you look at this lower graphic at the bottom, between test point 0 and test point 5, you can see that the linear passive channel is not including the transmitter or the receiver, but it is including the connectors, in this case backplane connectors, between the daughter card and the backplane. You never want to split a connector pair like this and try and put the reference plane in the middle. You always want to put it outside of that plug receptacle pair. When you look at this 802.3 AP, this Annex 69B is just an example of many of these terms that I've spoken about already. Insertion loss, fitted insertion loss deviation, attenuation, and these are all very, very specific to that channel that I discussed previously, not including the transmitter and receiver, but just the differential pair of the passive nature. And in addition, this is not just for the backplane daughter card. For any component board, back panel, connector, or via holes can be looked at in the same fashion. So one thing that I'd like to have you think about is the U.S. Air Force had done studies on F-15 fighter pilot attenuation or attention span inside the cockpit, and they found that it was very easy to overload the pilot with all of his sensory perceptions because there are so many gauges and dials and knobs and displays to keep track of during the flight time, especially if there's a fighter in back of him. Well, I think that there's a very clear analogous situation for signal integrity engineers in the SI lab that have so many tools that they need to keep track of. It's very easy to become saturated and become overwhelmed with so many tools. And so one of our strategies Agilent Technologies is using to help the signal integrity engineer is to simplify these tools, and we found that a very effective way to do this is to integrate the tools amongst each other. And so what we've done exactly for this purpose is we've integrated MATLAB into physical layer test system software. So you don't need to do this outside of that realm. And so what I'd like to do is to actually show you a demonstration of how this works. So what I'm going to do now is I'm going to spin up PLTS, and when we open up the PLTS, I'm going to import a file that is the MATLAB script. Actually, this is the data, excuse me. This is a balanced transmission line from 10 megahertz to 20 gigahertz, and it's a 4-port S parameter file, as you can see here. And when I open this, I'm going to open it up in frequency domain balanced, and we're going to have those 16 differential S parameters that I spoke about. Here is the quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Remember, quadrant 1 was the differential input, differential output. Quadrant 4 was the common stimulus, common response. And then quadrants 2 and 3 were the mixed mode quadrants. And so now what we're going to do is I'm going to create a new template for this fitted insertion loss and insertion loss deviation. So once I'm going to do the programming, and then we're going to save the programming in the template so we can leverage that in the future. So we're going to go to frequency domain balanced, and I'm going to look at differential insertion loss, and then also the reverse insertion loss. So once we look at the differential insertion loss, then what we're going to do is go to Tools, Math, Collaborate with MATLAB, and here, this is where we browse and we find the MATLAB code that we're going to leverage, CEI fitted insertion loss. And so this is the actual MATLAB code, the .m formatted file. And now what I need to do is map the device under test data with the MATLAB variables. And so I'm going to do that here with a few button clicks. And the first result I'm going to use is ILmin. And so now I'm going to save these formulas. And this one I'm going to call ILmin and save that one. Then we're going to push this over and we're going to go ILmax. Save that one. And then we're going to push that back and we're going to go to STD21. This is going to be DB. Save that one. And IL fitted. Save that one. And those are for the fitted, curve fitting polynomials that we saw in the previous slides. Now what I'm going to do is the insertion loss deviation formulas. And so for that we have insertion loss deviation min. Save that formula, push that back over here, and then insertion loss deviation max. Save that formula, and then one more is just overall insertion loss deviation. And save those. Okay, so we've done all of the mapping of the MATLAB variables, and so I can close that, and I'm going to apply them now. So I go Math, Apply, you get this dialog box here. First thing I need to do though is I need to put this in the real format. So if I go to this bottom left hand corner here, I can see these buttons, and if I hover over that one there, it says real, and it turns my differential insertion loss into real format. And now I can apply my MATLAB equations. The first time I hit apply, it's going to spin up the MATLAB compiler in the background of PLTS, and it'll take a couple seconds. But then every one thereafter is done immediately. There's no more spinning up of MATLAB. It's already spun up. And so this is for the insertion loss deviation. And so here we can do an auto scale on this, and that looks very good. So in fact, now what we can do is we can go in here and rename the plot, and we can call this CEI fitted insertion loss. And now we're going to go to the other plot, and we're going to apply the other equations for insertion loss deviation. Apply that one. Apply ID max and insertion loss deviation. We can do an auto scale on that one, and then we're going to call this, rename this plot, we'll call it CEI insertion loss deviation. Okay, so now what we can do is we can go here and we can save this template. We're going to say save template as CEI insertion loss and insertion loss deviation. So now what we can do is we can close all these files and open from the very beginning that same file, that balanced transmission line from 10 megahertz to 20 gigahertz, and open that up. And now, instead of opening it up in the frequency domain balance like we did before, we can scroll down and we can just open it up with the CEI insertion loss and insertion loss deviation template that we just programmed from that MATLAB script. And now you can see all of that programming that we did and saved it inside PLTS. We now have it as a template that we can use time and time again and save all of this time from reformatting and opening and going through all the MATLAB each time. So this is the idea of why we were talking about tool integration. And so what I'd like to do now is I'd like to finish up and give a conclusion. So here is the N1930B physical layer test system that we just went through, opening up a file and utilized the MATLAB scripting feature that's new for 2012. And we'd like to thank you for your time today and encourage you to visit our website that has many new videos, information, application notes, configuration guides, etc. And I'm Mike Resso, and you can see us at DesignCon, or anytime you can send us an email and we'll be glad to help you with your future application requirements. Thank you.